Here is an example based on the transformer, a practical transformer, a real transformer. So the given data is, here is a 100 kVA, 100 turns ratio single phase distribution transformer. When you see this 100:1, that means if you have 100 volts on the primary side, secondary side is only 1 volt. So it's a step down transformer. It's a distribution transformer, is operating at full load at 0.8 power factor lagging with 120 volts at the load. So if you draw the equivalent circuit diagram, I'll talk about it in a second. Let me finish reading this. 120 volts at the load. R1 is 25 ohms, X1 is 50 ohms, R2 is 0.006 ohms, X2 is 0.004 ohms, RC is 50 kilo ohms, XM is 60 kilo ohms. So this R1 represents the resistance of the primary winding, reactance of X1 represents the reactance of the primary winding, R2 represents resistance of the secondary winding, X2 represents reactance of the secondary winding, RC resistance of the core, XM represents the leakage reactance. Okay, find the applied voltage on the primary side, total impedance looking at the secondary side, voltage regulation and efficiency of the transformer. So he's asking about draw the equivalent circuit after transferring this entire primary side transformer into the secondary side. He's also asking about what is the supply voltage V1 right here. Okay, find the V1. He's also asking about find the efficiency, voltage regulation, 3 of those quantities. Okay, he gave us this is 0.8 lagging power factor. Okay, 0.8 lagging power factor, and he also gave us the voltage across this is 120 volts. Voltage drop across the load is 120 volts. Based on that, I can find the current passing through that circuit. Okay, now anyway, first what I'm going to do, I'm going to transfer this entire thing on to the secondary side. So that's what he's asking about, total impedance looking at the secondary side. So transfer everything into the secondary side. Okay, so first thing we need to do is find K value. Okay, K, some books indicates K, some books indicates N equal to N2 over N1. So basically this is N1 is to N2. N2 over N1 is nothing but 1 over 100, which is 0.01. That is the N value. Now we are going to transfer this primary impedance onto the secondary side. Remember, when you're moving this into the secondary side, we're going to call that as R1 prime. R1 prime equal to R1 times N square. Okay, so the R1 prime indicates equivalent resistance of the primary after transferring it to the secondary. So R prime is the equivalent resistance of the primary after transferring onto the secondary side. So R prime or R1 prime equal to R1, which is 25 times N square is nothing but 0.01 whole square. Okay, so this value is 0.0025 ohms. Same way we can write down X1 prime. X1 prime is also same thing, 50 times 0.01 whole square. So X1 prime is nothing but equivalent reactance of the primary after transferring it onto the secondary side. So this value is also going to be 0.005 ohm. Okay, this must be, X must be a reactance, so it must have a J term. I'm not indicating it here, I'm not showing it to you here. Otherwise, to avoid confusion, let me do this. So the J term, the X term is always imaginary term. Okay, same way you're going to have R0 or RC prime. Some books indicates R0, some books indicates RC, so I'm going to say both. So 50K times 0.01 whole square, which equal to 5 ohms, and xm prime equal to 60k times 0.01 whole square. Okay, this value is 6 ohm. Okay, as I mentioned, if needed, you can indicate with a complex number. So that's a complex part. Okay, now I'm going to draw the equivalent circuit referred to the secondary side. Here is the equivalent circuit looking from the secondary side. So this value is, this is 5 ohms, this is J6 ohm, and R2 we didn't change anything, so R2 value is 0.006, and this is J.004. I believe that's 004. Did I copy it wrong? Yep, that's a 004. I copied it wrong here. Okay, so that's a 004.004. I don't know the ZL, but I can find that ZL value. It's not too difficult because I know this value. The voltage across this is given. Voltage across the load is given. As well as the power consumed by the load is given. He mentioned clearly it is operating at full load with 0.8 power factor. So the transformer is fully loaded and S value is given 100 kVA. The 100 kVA S equal to 100 kVA. So it is fully loaded. So what is the power value? P equal to S times cos theta. Okay. So S is 100 kVA and cos theta is 0.8. So it must be 80 kilowatt. This is fully loaded. If it is half load, 50 times 0.8. So it's 40 kilowatt. So based on this, I can find I2, the current passing through this. I2 equal to S over 120, 100K over 120, that is 833.33 ampere. That is the current passing through the circuit. Now, to further simplify it, we call this current as probably I1 prime, and then I0, and then I2. Okay, when we compare I0 and I2, I1 prime is approximately equal to I2. That I0 is very small, that's what I meant to say. And you can clearly see the impedance is very small, so the current passing through this must be small. Even I can find the load impedance if needed. My load impedance GL equal to 120 over I2. That will give me my impedance. So I2 equal to 120 over 833.33. There is a phase angle. That phase angle comes from this theta equal to cos inverse of 0.8 from the power factor. I mean, the phase angle comes from the power factor. So cos inverse of 0.8 is 36.86 degrees. So this is minus 36.86. Why is it minus? Because he clearly mentioned that's a lagging power factor. If it is leading power factor, that's going to be plus. Lagging power factor, that must be minus. So ZL equal to 0.4144 at an angle of 36.86 degrees. That's my load impedance. Okay, even the load impedance, you can see that's a very small number compared to 5 ohms and 6 ohms. That's the reason my I2 is very large compared to I0. So to further simplify, what we can do, since the I0 is very small and I1 is approximately equal to I2, I can move this parallel branch to the other side. That makes our calculations a little bit simple. Okay, so we have R1 prime, JX1 prime, R2 and X2 and ZL. Okay, and at the same time we have R0 prime and X0 prime. So here ZL equal to 0.144 at an angle of 36.86 degrees. Now R1 prime, JX1 prime, we have those values as 0.0025, J 0.005, 0.0025, J 0.005. So here is the equivalent circuit. What we did, all the impedance on the primary side we moved to the secondary side. Okay, so this is 5 ohms, this is 6 ohms, J6 ohm. Okay, now I can add these two together. So we call that as total impedance on the secondary. We call that as Z02, which is nothing but 0.0025 plus 0.006. So the Z equivalent, which is Z02, is equivalent impedance of the transformer looking from the secondary side. So to find the Z equivalent, we can see 5 and J6, these two are in parallel. This parallel combination is parallel with this whole thing. Okay, Z02 plus ZL. Okay, Z02 plus ZL. Now since these two are in series, I added them. It is 0.1237 plus J 0.0954. Now I just did this parallel combination, 5 parallel with J6. I end up with 3.841 at an angle of 39.8. Now when I convert that into rectangular format, 2.95 plus J 2.458. Now this 2.95 plus J 2.458 parallel with this. Okay, so now I have two complex numbers that are in parallel. It is a little bit very long process to solve it. It's just Z1 parallel with Z2. How do you do that? Z1 times Z2 over Z1 plus Z2. This is the Z equivalent. I followed the same process and end up with finding Z equivalent as 0.15 at an angle of 37.72. That is the total impedance looking from the secondary side of the transformer. Now we'll find voltage regulation as well as the efficiency. Now when it comes to the voltage regulation, now we know the voltage at this point is 120 volts. So I know I can find that current. Actually I already did that. I2 equal to 833.33 at an angle of minus 36.86. How did I get this minus 36.86? He gave us this cos theta equal to 0.8. So theta is cos inverse of 0.8. This power factor cos theta indicates the angle between the voltage, this 120 volts, and the current. So that's what it is. Okay. Now from this I can find the voltage drop here. Okay. So I'll find the voltage drop. V drop equal to same I2 times Z02. Okay, I2 I have 833.33 at an angle of minus 36.86, and Z02 is 0.0085 plus J 0.009. Let me see. I don't have the conversion, so I'm going to convert that. I mean, this is in rectangular format. I'm looking for polar format. Let me write down in polar format. So here we voltage drop across this internal impedance of the transformer is I2 times Z02. So I2, I have that value is 833.33 at an angle of minus 36.86, and Z02, as that's the impedance of that internal transformer, 0.0085 plus J 0.009. Now after multiplying that, that's the total voltage drop across the impedance, internal impedance of the transformer. Now I'm going to find E value. So percentage regulation. First let me write down the percentage regulation. Voltage regulation is always a percentage. V no load minus V full load over V full load times 100. Okay. What is V no load? V no load equal to V full load plus V drop, voltage drop across the internal impedance. I have V full load as 120 at an angle of 0, and I have V drop as 10.25 at an angle of 9.77. Okay, now I'm going to convert this into polar format. This will be 120 plus a 0. Sorry, this is in the polar format. I'm going to convert this into rectangular format, which is 10.10 plus j 1.74. Okay, this is no load voltage. So if I convert everything into polar format again, the total is 130.1 plus j 1.74. This is 130.11 at an angle of 0.766 degrees. This angle is very small, we can neglect it. So the V no load voltage is 130 percentage regulation, voltage regulation equal to voltage regulation 130.11 minus 120 over 120 times 100. This is 8.425%. That is the voltage regulation of the transformer. Now we'll find efficiency. Efficiency equal to P out over P input. Okay, output power over input power. Output power we already know, 80 kilowatt. Okay, and input power is nothing but P out plus losses, P losses. Here he didn't give us the constant losses. What are the iron losses? So all I'm going to do, I'm going to find those iron losses. We cannot calculate with the given data. It must be given, the iron losses. So these losses are going to have Cu losses, which are copper, plus iron losses. Most of the time iron losses they will provide, but we can calculate the copper losses. Copper losses are nothing but the losses happening in the windings. Okay, P copper losses. We'll find the copper losses. When it comes to the copper losses, where is the copper winding in this transformer? So I see here is a, wherever you see resistance, that's a copper wire. That's where one, this is another one. Okay, I know the current passing through this is 833.33 ampere. Okay, and how about the current here? I can find that current because I already know the voltage here is 130.11 volt. Okay, so I'm going to say this is IW equal to 130.11 divided by 5. That will give us the IW, which is current passing through that core. The current passing through the core is 26.022 amperes. So the P copper losses, actually that's the copper loss. This comes under still iron loss because that's the core losses. Okay, but I don't know the losses here, so that's the reason part of it I don't know, the hysteresis losses. These are probably representing the eddy current losses. So P losses equal to I square times R. I have I square, which is 26.022 whole square times R is 5 plus 833.33 whole square times, what is that resistance there? That value is 0.0085. Okay, 0.0085. So these total losses are, so 3,385 of these losses and 5,902 of the copper losses. This is the copper loss. Probably I'll consider that's a part of iron loss. So efficiency is output, which is 80 kilowatt divided by input is 80 kilowatt plus, if I convert this into kilowatt, 3.385, I can say 3.4 plus 5.9, I can say approximately 6 kilowatt. Everything is in kilowatt. So the efficiency times 100, that will give you efficiency in percentage. Efficiency is 89.48%. That's the efficiency, and voltage regulation is 8.425. Okay, so this is how we'll find equivalent circuit as well as efficiency and voltage regulation of a transformer. I'm going to solve at least another example, similar example. Okay, thank you.